This one summarize for you lah, what we are going to cover lah. Magnetic field due to currents. Page 168. Right, there's a syllabus. I think they have make it simpler, this one. Explain the origin of the forces between current carrying conductor and determine direction of the forces. Right, no need to calculate, I think. Okay, current carrying conductor. There's a magnetic field around a current carrying conductor. Just a wire, like you like. By plotting the field using a plotting compass on a paper to reach the current flow, we are interested in the field of long straight wire, loop or flat circular coil, long solenoid. Okay, magnetic field lines of a long straight wire. I is the current coming out of the page. This is I coming out of the page. Right, magnetic field around a current carrying wire. A moving charge produces a magnetic field around itself. Circular path becomes further and further away, right? Showing there is a non-uniform field. Right? We use the right-hand grip rule. We'll come into it in a while, where the thumb represents the current coming out and direction given by the fingers. Fingers. These are concentric circle with the current carrying conductor at the center. Right? What is wrong with this diagram? Any idea? What's wrong with this diagram? Anything wrong with the diagram?
Is it the wire?
Nothing wrong with the
All
wire.
circular.
Three lines are circular path with wire at the center. That is correct. What's wrong with the diagram? It shows that it's uniform field. Right? The circle should be further and further apart. Concentric circles are closer near the wire, where the field is stronger, and further apart, where the field is weaker, away from the wire. Right? Wire diagram shows the field is uniform. Field varies inversely as the distance from the wire. Right? What is meant by long wire? R is the distance from the wire. L is the length. So it means that your length must be very much greater than R. Right? You can use plotting compass, plot the field. That's how the field looks like. Sketch the field lines of a long straight wire. I is a current coming out of the page. Right? It's coming out of the page. So it's anti-clockwise. This one is going inside the page, the current. So it's clockwise. Right? Closer together, near the wire, further apart. Show a weaker field. Right? Don't worry about the formula, it's not required anymore. Magnetic flux density is perpendicular to the distance r away from the wire carrying a current I. Right? As I said, no need to worry. I think the syllabus doesn't mention this anymore. So you don't need to know about the formula. You don't need to know how to use the formula also. I won't bother about this one, and also right, no need to know that also. As I said, no need to worry about the formula. Magnetic flux density depends on the current. Right? It's the current that produces a B, so it must be related to I. More current, more field. Distance from the wire, the further away it is, the weaker will be the field. Medium is this one, permeability of free space. Yeah, that's the medium. Right? Don't worry about this one also. Okay, direction of magnetic field. Magnetic field lines or lines of force can be drawn around a current carrying conductor. Direction of field lines depends on the direction of the current in the wire. Direction of the line of force can be found by Maxwell corkscrew rule or right-hand curve rule. Here's a right-hand curve rule. The thumb represents pointing to the direction of the current. So the finger shows the direction of the field. I want to show you that. Okay. Don't worry about corkscrew rule lah. Just use the right-hand curve rule, good enough lah. Corkscrew. There's your corkscrew. This is just for info lah. Where we define our intensity for light times the area, surface area of the circle equals to power. Right? Intensity is the energy per unit time falling normally per unit area on the surface. Right? For charge, do the same thing. It's a circle, electric field outside a distant r away of the sphere. Right? It's a 4 pi. That is your surface area of the circle. There's a charge inside the circle with epsilon naught. Right? Whereas for magnetic field, you use mu lah. Instead of epsilon, you use mu. Permeability, that's the current. Right? As I said, don't need to worry about all this formula, just to show you the symmetry, that's all. That's B times 2 pi R. What's inside the circle is your mu naught over I. Okay, let's go to flat coil or a loop. There can be many turns, doesn't have to be one turn. The side view, taken from this side. R is the radius of the loop. As I said, no need to worry about the formula anymore. Not required to know how to use it also. Factors affecting electric field strength at the center here, B. There are two ways to increase the field of the magnetic field strength. Increasing the current, right? Remember the current affects B. Increase the number of turns, number of coil, number of turns. Decrease the radius of the loop. Right? Make this radius smaller, then it's stronger there at the center here. Right? That is how you can use your Hall prop for your information to find out how the field varies with distance from one side to the other side. That's how roughly how the graph will look like. Right, this is for info. Your loop radius R, and then there's a radius. So the field within the two loops is uniform. That's how we get uniform field. Okay, long solenoid. Right, this is insulated copper wire. Right, there's your north pole. Right, there's your north pole. There's your south pole. This is the current balance. I hope your teacher has Like you all do it in your class. This is your coil. The coil is positioned so that there's attractive force between the north and south. And you add mass here, or you shift the mass. You shift the mass until it becomes horizontal again. Solenoid is made up of several turns of wire in the form of a cylinder. That's how a solenoid looks like. When current flows through the solenoid, the magnetic field formed around the solenoid is identical to the bar magnet. Same as a bar magnet. Right? Except bar magnet, it doesn't go through the inside there. Same, similar. Inside the solenoid, the lines are parallel. That means show is uniform. Within here is uniform. Outside it becomes non-uniform. As the lines move outwards with the open end, they spread out, becomes non-uniform. Right? This part is non-uniform. This part within is uniform. This part is non-uniform. Here's a comparison. The field is stronger at the center, right? Because it's uniform, and decreases to half at the end, and decrease further as you go further and further away. It becomes smaller and smaller. Right? Same number of field are spread out over a larger area here. Unlike bar magnet, the field lines pass through the solenoid, pass through the middle of solenoid. Magnet, it doesn't pass through. Okay, polarity. How do we get a polarity? Yeah, fingers. For long solenoid, the length is much longer than the diameter of the solenoid. The field is uniform near the center of the solenoid. Okay, that's the diameter of the solenoid. That's the length of the solenoid. As I said, don't worry about formula. No more required. Right? Summary, electric field strength can be increased by increasing the current. That's the first thing. Current is the one that produces a field. Increase the number of turns per unit length of the solenoid using a soft iron core within the solenoid. Ferromagnetic material, example, iron, steel, cobalt, nickel, placed in solenoid increase greatly the magnetic field strength. That's an electromagnet. That's a commercial one. Okay, determine the pole of the magnet. The pole of the magnetic field of a solenoid can be determined by the right-hand grip rule. Right-hand grip rule. Here, you grip it. Your fingers show the direction of the current, and the thumb points to where the north pole is. Okay, right, grip it. The fingers shows the direction of the current, direction of the north pole. The thumb shows the direction of the north pole. Alternatively, you look at the end of the pole there. It is clockwise, it's south pole. If it's anti-clockwise, right, then it's north pole. Okay, any comment?
No.
Right, that's happened now. Same as stick, a bundle of stick, right, where you tie it up, they are straight. At the end there, they tend to branch out, right, to space out into more area. Okay, what's the polarity? Which is north pole, which is south pole? Yep, yep. Which is north pole, which is south pole? Both follow.
North is at the left hand side. The
Left
town
hand side.
facing north.
Okay. As I said, don't worry about that. Don't worry about this one, how the magnetic field changes within in uniform inside as it goes out, it decreases. So don't worry about all this. Okay, summarize for you. Ferromagnetic material, example, iron, steel, copper, nickel, placed in solenoid, concentrate, and thus increase greatly the magnetic field strength. Used in electromagnet, right? Electric motor applications like dumping shade garbage through powerful magnetic field to sort out and recycle metal bits. We got garbage, paper, and metal. They use electromagnet to attract the metal. Right? Ferromagnetic material can be magnetized in magnetic field. Steel becomes a permanent magnet. Iron becomes a temporary magnet. That means it loses its magnetism when the field is switched off. Right? We call it soft magnetic material. Right? Non-ferromagnetic material, example, aluminum and copper. Remember, not all metal are ferromagnetic material. Right? Copper and aluminum are non-ferromagnetic material, cannot be magnetized in magnetic field. Okay, this used to be popular deriving the equation, but I don't think they would ask you to do. Yeah, these are the years that they come out because you don't need to know the formula already. Okay, like current attract. Right? These are the magnetic force. Current carrying conductor, magnetic force attract each other. Opposite to charges are like charges repel, like current attract. Right? Just to show you the derivation, they will have to give you the formula lah, and explain to you what is mu naught lah. Right? There's a formula for the field due to this conductor, due to this current conductor at a distance r away. Right? If you put a conductor there, right? The field is due to this current conductor. We are going to derive this formula lah. Most likely it's normal in the syllabus lah. But you need to know that the force is magnetic force lah. Right? If there's a current, the wire 1, then it flows the wire 2. Right? Wire 2 carry a current, distance apart is D, carry a current in the same direction I2. So the force is B I2L. That one is in the syllabus lah. Right? You can think of that as your L. Right? That's your mu naught. That must be given you. If they want to ask you to derive, that must be given you for that one. 10 times I2L. Then force per unit length is this. Okay, that formula. Any comment? Anything not clear?
Yeah, can.
Force on wire 2 in magnetic field B. Right? Magnetic field is contributed by current carrying conductor wire 1. Right? This wire 2. The wire 2 carry a current in the magnetic of wire 1. It's just a repeat. Just to show you that if we look at 2 dimension, the field is circular. Right? Going inside, going into the page or the slide. Right? I1 and I2 I and I2 are action and reaction force. Okay?
Yeah.
Forces are action and reaction force. They are magnetic force. Okay, comparison between electric, magnetic, and gravitational force. Info, just for info. Electric field, a charged mass experience a force. Positive charge mass move in the direction of the field, while a negative charge move in opposite direction. Let's summarize for you in the diagram. Positive charge move direction of electric field. Same as gravitational field. Uncharged mass, this uncharged mass, experience a force, and the force on the mass is the direction of the field. You drop the mass. The mass is in the direction of the field. Whereas magnetic field, there's no force. Whether it's stationary or moving in the direction of the field, there's no force. Right? In magnetic field, a charged mass experience a force only when the mass is moving at an angle to the field. Right? It's moving at an angle, parallel, no force. Magnetic field, there's no force on the charged mass when it's stationary or moving in the direction of the field. Right? It must be at an angle to the field. Okay, I want to summarize for you what this topic is all about. Okay, summarize for you what we have learned, previous topic, then Hall effect, Hall effect, how to derive it, velocity selector. Okay, let's try some question. Page 184. Two long straight current carrying conductor PQ XY, PQ XY are held a distance apart as shown in figure 6.1. The conductor each carry a same magnitude current in the same direction, current in the same direction, same magnitude. This one can come out. Plane view from above, shown in figure 6.2. Draw on figure 6.2 arrows in each case to show direction of magnetic field at Q due to carrying conductor.
Anti-clockwise.
Yeah.
Is it anti-clockwise?
Draw arrows, one on each case to show direction of the magnetic field at Q due to current carrying. Right? This is the one that carry the current. What's the field here at Q? At Q? At Q, what is it? It's anti-clockwise, but we want to know the direction of field at Q.
Yeah, meaning like
Up,
north, south, east,
right,
west direction.
right? Remember, it's a circle. It's a circle,
Yeah, circle.
right? Concentric circle. So by the time it reach Q, it is going to be that one. Downwards. There's a B. Okay? The force at Q as a result of magnetic field due to current carrying conductor XY, label the force F. Where's the force? Use your left hand rule, or if not, you remember.
Force is towards us. Wait, up.
Either you use Fleming's second rule or you memorize it, like current attract it. Then current
Wait,
coming
where's
out,
the arrow?
current coming out,
Coming like towards
field
us,
going
right?
down. So where's the direction of the force? Field is going down. Current is coming out.
To the right?
To the right. Oh. That's all. Just right like that.
Hmm.
This one can come out. Take Newton's third law of motion. And this one can also come out because they require you to know its action and reaction force. When two bodies, right, where is overlap can come out Two bodies interact, force on one body is equal, but opposite to the direction of the force on the other body. Use the law to answer A part 2 to state the direction of the force on wire XY. Yeah. They ask you to state, so they want you to use the law. Attractive force,
Uh,
same
yeah.
attractive
Uh,
force. Yeah, attractive force. Opposite direction to one in A2, both forces are action and reaction force. Okay, so it's
yes.
attractive force. Okay, you can draw it up if you don't want to state it. Okay, now I'm testing you. On figure 6.2, draw arrows, one in each case to show the action of magnetic field Y due to current in the wire PX. Label this B. This is a current carrying conductor. We want the field here. Where is it? Yep. Same diagram. We're using the same diagram. Except now the current is here. This is the one carrying the current. I'm asking for you the field around here. Yep. The field is concentric circle, anti-clockwise. So it will be that way. That's your field, BQ. Right? Due to current carrying conductor in Q. The force at Y as a result of the magnetic field due to the current in the right? That one we have done that already. That's your force, attractive force. Okay or not?
Yeah.
Hot air from an air dryer contains many faulty charged ions for 10 more minutes. Motion of these ions constitute electric current. The hot air is directed towards the pole of the bar magnet as shown. What happens to the ions? 97 summer, long time ago. Just to test you, see whether you are not apply your knowledge.
What happens to the ions?
Yeah, A, B,
Uh,
C towards the deflected, they are deflected towards the north pole, they're deflected towards the south pole, they're deflected downwards, they're deflected outwards. Yep,
hot air.
the current is coming out, the field is going from north to south,
B.
donkey. Right? The field is going there. What's the field? There's a current. The field is from north to south. So it's only up or down only. So you have to use Fermi level rule to determine. Okay? Then
Yeah, I got it.
there's your field north to south, east to west. Current is coming out. So force hours. So, right? Donkey. How about this one? Horseshoe magnet rests on a top band balance with wire situated between the poles of a magnet. With no current in the wire, the reading is 1420.142 gram, and the current is 2 ampere in the wire in the direction of XY. The reading of the balance changes to 144 gram, 144.6 gram. What's the reading of the balance when the current is 3 in the wire in the direction of YX? Yep, a bit challenging. Ken, what's the answer? That's the current initial stage. So that the force is downwards. That's why there's an increase, right? Compared to this mass of the magnet, there's an increase. So the force must be downwards. Right? And that's the North Pole. Answer A. Ken,
Yeah.
yeah, just using this formula, these two formula, F is the same. Right? The others are constant. So you use delta M over I. Delta M over I, the others are constant. Right? Remember, F is a new mass. Okay, any comment?
Yeah.
A wire 3 meter long, mass 0.1 kilogram, and carrying a current 70 ampere floats without support above a horizontal wire 2 cm below and parallel to it. That's the diagram. Right? This one is floating above this wire. Find the current in the lower wire and its direction. Then
Mm,
this is more challenging. Right? They have to give you the formula. Right? There's a current. Right? Then it's 3 meter. Separation is right? 2 cm, change it to meter. Right? That's the weight of the wire. So for it to hold to be floating upwards there, the force must be the magnetic force must be repulsive. Right? Magnetic force balance the weight. Right? We're just using this equation. Right? That one is in the formula sheet. No more already. Don't have to worry already. It's just to show you. Right? 70 I times I2. That's the I2. Right? That's your weight. Right? This is force per unit length. Right? The weight is just set divided by 3, force per unit length. Okay. Let's try past year paper. You can try the rest yourself. What is meant by magnetic field? Can Yep. What's meant by magnetic field?
Uh,
Region of space where there is a force acting on a current carrying conductor or magnet. A charged particle of mass m and charge q traveling with velocity v in vacuum. It enters a region of uniform magnetic field of frequency b, as shown in figure 5.1. The magnetic field is normal to the motion of the charged particle. The path of the particle in the field is an arc of a circle or radius r. Just in case you forgotten them. Right? That's how it looks like. Explain why the path of the particle in the field is an arc of a circle. Yep. Force on particle is always normal to velocity, and the speed of the particle is constant. Right? Derive the equation, the expression, magnetic force equals to centripetal force. Right? That's important. This point must be there. Or this one. Either one is 1 mark. We cancel all. Okay.
yes.
A thin metal foil is placed in the magnetic field in B. A second charged particle enters the region of magnetic field. It loses its kinetic energy as it passes through the foil. The particle follows the path in figure 5.2. On figure 5.2, mark the arrow direction of travel of the particle. Where's the direction of travel of the particle? Can particle move through the foil, it loses kinetic energy, velocity decreases, radius would be smaller, right? So that is where the particle enters. So. Can or not?
Yes.
Right? They are required to use this formula. Path of particle has a different radii for each of the foil. The radii is 7.4 and 5.1. Ratio of final momentum of